My name is David Hoey, and I'm an Associate Professor in Biomedical Engineering here in Trinity College Dublin. My undergraduate training is in Mechanical and Manufacturing Engineering, but it was only towards the latter stages of my undergraduate degree that I became exposed to biomedical engineering, which is really just using mechanical engineering principles to look at biology and medicine. And that kind of fascinated me because I was always very much interested in how the human body worked. My main research area is bone and trying to find new ways to regenerate or repair bone. Specifically for me and my group, we're very much interested in how physical exercise can regulate skeletal health, so the bones of your skeleton. The more you exercise, the bigger and stronger your bones are, but the opposite is also true. So for example, if you were an astronaut, you're going into zero gravity, your bones aren't being loaded as much. As a consequence, you tend to lose bone. And one of the main, bone diseases is osteoporosis, which is a bone loss disease and characterized by low bone density, which results in an increased risk of fracture. So for example, 1 in 3 women and 1 in 5 men over 50 will suffer an osteoporosis-related fracture in their lifetime, which corresponds to about a fracture every 30 seconds in the EU. So under the COFUND program, my research was mainly looking at trying to decipher how our bones can respond to exercise in terms of essentially making more bone and having healthier bone. And we've known that this happens for quite a while, but we don't understand how cells within our bones, such as mesenchymal stem cells, how they actually sense that exercise. And one thing we were looking at is that these cells have little cellular structures sticking out from their surface called, not unlike an antenna, called a primary cilium. And what we found was that when you're exercising, you're essentially bending this antenna, and that is like a switch that tells the cell that it's being exercised and therefore starts to form bone. But through our research, if we can understand the fundamental mechanisms by which loading can actually promote bone, then maybe we can develop new ways to actually enhance bone without actually going for that exercise, which is important for somebody who already has weak bones and can't do that exercise in the first place. As part of the Marie Curie COFUND program, I got to travel to Columbia University in the city of New York to work with Professor Chris Jacobs, who really was a world leader in experimental bone mechanobiology. But it wasn't just Professor Jacobs. You're working in the Department of Biomedical Engineering in Columbia University, where you have not just one, but you have several. Nearly everybody is a world leader in their space. So getting to see how they think and what they do and how they approach problems was incredibly rewarding, and you would learn a lot very quickly in an environment like that. I was fortunate enough, a year after my COFUND, to be awarded a European Research Council starting grant, which has really allowed me to kind of transition to independence and build a research team around me to continue that research I started during my Marie Curie experience. Now, I'm a big advocate of the COFUND program, particularly the mobility element of it. I think it's a really clever idea to send people away and to learn new skills and experience new environments. And that's one thing that I really took from going abroad, going to Ivy League universities and seeing how they think and how they approach problems. I mean, it does change you in terms of how you see things, and then be able to learn those new skills, take that knowledge and bring it back to Europe, to Ireland, for example, and implement that here. I think that's a very effective way of developing the next generation of researchers.